Hello everyone, this is Professor Roman. Welcome to the 35th lecture in my course An Introduction to Discrete Mathematics. In this video, we're going to discuss another decomposition, in this case, partitions of an integer. We saw earlier, it was theorem 358, that the distributions of k distinguishable balls into n indistinguishable boxes with no box empty are in one-to-one correspondence with the partitions of a set of size k, the ball label set, into n blocks that correspond to the boxes. Also, this number of partitions or number of distributions is the Stirling number of the second kind. Now let's consider the placing of k indistinguishable balls into n indistinguishable boxes. So they're both indistinguishable, again with no box empty. When the balls were distinguishable, as I just said, the distribution corresponded to partition of the ball label set. But now we don't have any ball labels because the balls are indistinguishable. So we cannot make sense out of which ball goes into a box. All we can say is how many balls go into each box. So, for example, if we have 7 balls and 3 boxes, then here are the possibilities for distributing those balls into boxes. 5 balls into one box, 1 ball into, might be better to say another box, and 1 ball into another box. Or 4 balls into one box, 2 balls into another box, and 1 ball into another box. So 5, 1 and 1, 4, 2 and 1, 3, 3 and 1, 3, 2 and 2. Now, since the balls are indistinguishable, the boxes are indistinguishable, we can make a list in any order we want of the 3 numbers. The numbers are referred to as the occupancy numbers of each box. And the collection of box occupancy numbers is a multiset of n different integers whose sum is equal to k. Here are the multisets, 5, 1, 1, 4, 2, 1, and so on, corresponding to these distributions. There are 3 numbers because there are 3 boxes. There's the sum of the occupancy numbers has to be k. That's the total number of balls. To emphasize that fact, that the sum has to be k, it's customary, rather than writing multisets, to write actual sums. 7 is 5 plus 1 plus 1. 7 is 4 plus 2 plus 1, and so on. So, in general, the distributions of k indistinguishable balls into n indistinguishable boxes with no box empty corresponds bijectively to the ways that we can write the integer k as a sum of n positive integers. And because the order that we write the terms in the sum doesn't matter, because the boxes are indistinguishable, it's customary to write the terms in decreasing order. I think some authors may use increasing order. I'm not sure about that. But we'll stick with decreasing order. The order doesn't matter, so we don't have to, but in general we will. So now we're ready to define another type of decomposition, the analog of partitioning a set into the union of blocks or decomposing a permutation of the product of cycles. Here we have a partition of a positive integer. And it's simply a sum of terms that are positive. Everything's an integer, of course. Each term is called a part of the partition. And as is customary, we write the parts in decreasing order of magnitude. I'm going to denote the set of all partitions of K into n parts by part Kn, and little p Kn is the number of those partitions. And part K is the set of all partitions of the integer K, regardless of the number of parts. And I'll use P of K for that size. So for example, here is a complete list of part 5. And this list is not that difficult to construct if you think in terms of magnitude of parts. So the largest part, possible part size, is 5, in which case there's only one part. So 5 equals 5. If the largest part size is 4, you have to have 4 plus 1. If the largest part size is 3, there's two possibilities, 3 plus 2, 3 plus 1 plus 1, and so on. When the largest part is 1, of course, all the parts are size 1. So here's the result so far. The distributions of K indistinguishable balls into N indistinguishable boxes with no box empty corresponds bijectively to the partitions of K into N parts. And the parts are the occupancy numbers of the box. So the number of distributions of K indistinguishable balls into N indistinguishable boxes with no box empty is equal to this number pKn. Well, now that we've taken care of that, we can set aside the balls into boxes model, and I never have to say again the number of distributions of K indistinguishable balls into N indistinguishable boxes with no box empty. That's a mouthful. And we'll just concentrate on partitions of an integer. It's not that the distribution model isn't important, it is, but it's, I guess in some sense, not as important as the partitions of an integer. Okay, so we'll use that terminology from now on. Well, the bad news is that there is no known formula for the numbers pKn. But they do have some, they're very important, and they do have some very interesting properties, beginning with the recurrence relation. So let's look at that now. The number pKn of partitions of K into N parts satisfies this recurrence. Now, the proof is going to use the same argument, mutatis mutandis, which is Latin for with the necessary changes, obviously, has to be in context. It's the same argument we used twice before for partitions of a set into a certain number of blocks and for decomposition of a permutation into a certain number of cycles. Same type of argument. So we're going to divide the partitions of K into N parts into two groups. Those that have a part equal to 1 and those that don't. And there's two ways to look at these, and I'm going to choose the different ways for the two different groups, and I'll show you what I mean. As to the first group, we can construct that group easily. For every partition of k minus 1 into n minus 1 parts, just add 1. So here's a partition of k minus 1 into n minus 1 parts. Add 1 to both sides, you get a partition of k into n parts, one of which is equal to 1. And this is obviously reversible. You just subtract 1. Or better to say, just remove the part of size 1. One of the parts of size 1. There could be others as well. And then that will take you from this partition back to this partition. So we have a bijection here, and the number of partitions of k into n parts that do have a part equal to 1 is therefore equal to this number of partitions of k minus 1 into n minus 1 parts. Okay, so we build the partitions we want from these partitions. For the second group, let's go the other direction. This is the kind of partition we want. This group are the partitions that don't have a part equal to 1, which means all the parts are at least size 2. If I have such a partition, I can subtract 1 from each part. That will give me a partition of k minus n also into n parts, because Rn, all of these r's are bigger than or equal to 2. When I subtract 1, the resulting parts are bigger than or equal to 1. This also goes back and forth. If I start with this, I just add 1 to each part, and I'll get this. So the number of partitions of this type, partitions of k into n parts that have no part equal to 1, is p k minus n n. And now we have to say something which I did not do, but I did before, to the effect that these two groups of partitions are exhaustive. They cover all partitions of the specified type, and they're mutually disjoint. There's no overlap. And so when we add this and this, we get, in fact, this. Well, this is kind of interesting. Some of the properties of the numbers pkn can be revealed to us by representing a partition as an arrangement of dots on a page. These are known as Farrer's diagrams. So, for example, here's a partition of 7, 3 plus 2 plus 1 plus 1. Because there are 4 parts, we're going to have 4 rows of dots. Each row has as many dots as the size of the part. 3 dots, 2 dots, 1 dot, 1 dot. A very simple picture, yet it yields a lot of interesting things. So the number of rows is the number of parts, and the total number of dots is the number we're partitioning. So there'll be k dots organized in n rows. Here's another example. I'm going to use this one later on, so I wanted to add it here. Okay, it's a little bigger, got a little more interesting property. first thing we can do with the Ferris diagram. The Ferris diagram of a partition, script P, of K into n parts can be flipped along its main diagonal. So that would be this dot, and this dot, and this dot. Those lie on the main diagonal. So we interchange the rows and the columns. This is the analog of taking the transpose of a matrix, which you would be familiar with if you took any linear algebra. The flipped diagram is also a Ferris diagram for a partition that I'll denote by script P with superscript C. It's a Ferris diagram for a partition of the same integer K because it's got the same number of dots. This partition, P sub super C, is called the conjugate partition of P. The conjugate partition has the property that its largest part size is equal to the number of rows or parts in the original partition. Let's look at that. Here's a partition, 3, 2, 1, 1. That's a partition of 7. Here's its conjugate. So the first column becomes the first row. Second column, second row. Third column, third row. The number of parts, 4, becomes the size of the largest part. Same thing here. The number of parts, which is 5, becomes the size of the largest part. So I should have mentioned this here. So 7 equals 3 plus 2 plus 1 plus 1 becomes 7 equals 4 plus 2 plus 1. And 13 equals 4 plus 3 plus 3 plus 2 plus 1. The conjugate partition, 5 plus 4 plus 3 plus 1. Different partitions in general, different number of parts in general. But some partitions are self-conjugate. They're equal to their own conjugate. And I left that for you to produce an example, okay, just for practice. Find a partition that's self-conjugate. Since conjugating twice, like taking the transpose twice, brings you back to where you started, the relation of being conjugate is symmetric. If P is conjugate to Q, then Q is conjugate to P. And so we can just say that two partitions are conjugate or not conjugate. The conjugacy map, which I'm calling theta sub k, I like theta, sends the partitions of k to itself. It takes the conjugate. This is its own inverse. This is a bijection on the set of partitions of k. Okay. Now, let's think about partitions where the size of the largest part is specified. So I'm going to use this notation. I'm not suggesting this is standard notation. I don't know whether anybody else uses it or not. Seems reasonable. Part k n m is the set of partitions of k into n parts where the largest part is m. So the top row of the Ferris diagram has m dots. Well, then, as we can see from these partitions here, okay, if P is a partition of k into n parts, largest part m, then its conjugate will have m rows or m parts, and the largest part will be n. In other words, the largest part and the number of parts interchange values. Okay. So let's look at this one. The largest part was 4. The number of parts was 5. Now the largest part is 5. The number of parts is 4. So you can just concentrate on the first row and first column. The rest doesn't matter. This number, which is the size of the largest part, becomes this number, the number of rows. And the number of rows becomes the size of the largest part. Okay. It's going to take a while. This stuff's not easy. It takes a while for it to sink in. Don't be discouraged if what I just said sounded like gibberish. It's okay. You just have to go over it enough times until it begins to sink in. So in symbols, if P is a partition of K with n parts, largest part m, the conjugate is also a partition of K, but now there are m parts, the largest of which is m. M and n swap places. And that's really not quite fair. It's not m and n, it's the value that changes, right? Okay. So another way to say this is that the conjugate function maps part k n m to part k m n. The point here is that these two sets have the same size. The number of partitions of k into n parts, largest one of which is m, and the number of partitions of k into m parts, the largest of which is n. They're not the same partitions, but there are the same number of partitions. If we look at this set here, obviously, if we have two different largest part values, we got two different partitions. A partition can't have largest part 5 and largest part 6. That's absurd. There's one largest size. Okay. There can be several parts of that largest size, but there's only one largest size. So the number of partitions of k into n parts is the pairwise disjoint union of these sets of partitions. So in other words, I can split up this set by largest part size. I can take all the partitions of k into n parts whose largest part size is k, and then whose largest part size is k minus 1, k minus 2, and so on. Those individual groups partition this set in the set sense. So this set is the disjoint union of these subsets. And the same thing works here. I'm using this notation to denote the set of all partitions of k whose largest part is m. So I'm not specifying the number of parts. It could be anything. But the largest part has to be m. This is also the disjoint union of these sets, or in other words, this set is partitioned in the set sense into these subsets. Now I got a little issue with using n and m in both these settings, so to try to make it as clear as possible what's coming, I took this equation and I interchanged n and m. Those are just symbols. I could have changed n to x and m to y. They wouldn't change the equation, right? As long as I do it consistently. So I've interchanged n and m, and the reason is for this step. The size or the number of partitions of k into n parts is, again, this sum. So that's what I have here. And because these two sizes are the same, when you swap n and m, I swapped n and m here. The summation is still the same, but this one is here now, so it's equal to this. So what does all this mean? Well, it's quite remarkable. This is what it means. The number of partitions of k into n parts, I don't need to say exactly, into n parts is equal to the number of partitions of k whose largest part is n. Number of all partitions, no matter how many parts there are. Okay. Here's an example that helped clarify this weird property. There are 4 partitions of 7 into 3 parts. So there are also 4 partitions of 7 into whatever number of parts that have largest part 3. So these are all 3s here in this first column here, right? And these are all the partitions. There are 4 of these. These are 4 partitions of 7 into 3 parts. There are 4 partitions of 7 into any number of parts that have largest part 3. So that's what I mean by the Farrer's diagram and conjugates can reveal some interesting things about these very elusive numbers that we don't have a formula for. Let me say this again because I know it can be confusing. I'll try to say it in a little different way. We're interested in the partitions of the integer k. And there are 2 parameters we could specify: the number of parts or the size of the largest part. We have 2 choices there. We could say the number of parts is n, or we could say the largest part is n. It doesn't matter which we say. We'll get different partitions, but we'll get the same number of partitions. So there are as many partitions of 7 into 3 parts as there are partitions of 7 that have largest part 3. Okay, I know this is kind of heavy going. It's a little abstract. It may take a while for this to soak in. Remember, I did say at the beginning of this chapter that this material was a bit more advanced and was optional for this course. This would be, it's going to get a little worse, I'm afraid. Try not to make it too much worse. Try to be as clear as I can. But it's going to get a little bit worse. So I think this might be a good time to stop this video. It's about almost 30 minutes long. Give you a chance to go over this video a couple of times if you need to. Get comfortable with this stuff before we move on. So thanks for watching this video. Hang in there, and I hope to see you in the next video.